Also, ich meine Kollegin ist unbedingt Problem. Also, na, es ist ein Blow. We can step down. Und mein Kollege macht Wasser und Luft.
Can I hear myself? This one? Okay, this looks okay. Can I still hear myself here? Hello, hello. It looks like everything is working. Hi, welcome back. We will continue today. I'll do a little bit of recap. So we started talking about these continuous systems in 1D. And last week we talked about the X and P basis. We'll do a recap of that. Then we'll spend some time building up, and it will be a bit just technical, mathematical. We'll be computing some commutators that we need. And then it will pay off when we finally start talking about Hamiltonians of like Euclidean space and seeing how the position and momentum evolve in time. And for this, we need all these ingredients. Okay, so in the beginning, it's going to be a bit dry, but then it gets better. So let's just recap where we were last time. And the lectures notes should be on Moodle like right now. So what did we do? We saw we could express a quantum state in one dimension in two different bases. I mean, there are infinitely many bases, but we care about these two in particular. This was the position basis, so this was the position wave function that we called here to these coefficients. And we can also express it in a different basis. With a different wave function, which sometimes I use, I think last week I used tilde of psi, but in the exercise in lecture notes, there's just a bar, so I just use this. Okay, it's just a symbol to tell us it's a different function from that. So this was what we call the momentum basis, and we'll see today why we call it the momentum basis. And this is the momentum wave function. This coefficients here, remember, it's just a number, complex number that depends on P. And then what was special about these two bases was that their inner product was this exponential of phi x, some constant, and here normalizing constant. Okay. And this we saw, maybe I will not do it explicitly now because we don't need, but we saw that we could see this wave function as a Fourier transform of this one and vice versa. In fact, this was the inverse Fourier transform of that by just plugging in this thing and vice versa, right? That's what we did. And then we introduced the operators, the observables, x and p. So x, and p was gp in the p basis. So x is diagonal in the x basis and p is diagonal in the momentum basis. And then we saw how to compute this, what's the average momentum for some state psi. Well, if psi is written in the position basis, it's very easy because it's just the average of this square of the wave function weighted by the value of this observable there. This we saw. But then we decided to also write it, if our state is not written in this basis, but is written in this basis, how can we write p as a function of the position wave function? And this was with some constant here, minus I h bar dx. And then it was much more complicated, so I spent a long time doing this. That's right. You will do the same in the tutorial. For this, just for training, if you want to do it, I mean, you don't have to, but just for training, it's exactly the same procedure as we did for P. You do it for X. And of course, it's going to be symmetric. You get a plus I there, but it's going to be symmetric. Good. Then the other thing that we did at the end of the lecture, and I'll recap a bit more now because I didn't tell you why we should care about this, was to see how these two things act on how these operators act on the wave functions. So I'll do P and X. X on the wave function. And why do we care? If you have, let's go back to the discrete case, right? If you want to know how a matrix acts on a state, so this is a matrix times a vector, okay? You just need to know what happens to these coefficients in a given basis, right? And this is exactly the same. Remember that the wave functions are just the coefficients when you expand the state in a given basis. So if I want to know how the operators act on the state, I just need to know what happens to these coefficients, which are the wave function. So more explicitly, so if I have the operator acting on a state, well, this is the operator acting on a state that I can express in a certain basis, for example, dx. Because everything is linear. With, sorry, x here, with this thing. But this is just a new state, right? Let's call this new state psi prime. And psi prime is something that I can expand again in the same basis, right? So I can expand psi prime in the x, and now there's a new wave function here. And by learning this thing, I learn what the effect of A is even on each basis vector, and I can see how it acts on any state. And how do we? So instead of writing just how a matrix acts on any given state, I can say how it acts on the coefficients for a given basis. So I can write like this. Well, here's my operator. It's not a matrix, but and it maps x to this a new wave function. And how do I find this new wave function? Well, this is kind of the definition of the wave function for the new state. And that's x. So we'll do this. This applies to operators in general, so they don't need to be unitary or Hermitian or anything. Just need to map vectors to vectors. They don't need, the new thing does not even need to be normalized. Okay, so this is why we care. And then we saw some examples, but I didn't do the simplest example, which is, well, how does momentum act, for example, in the position wave function? Okay. So we do it. How do we find this? This new thing is going to be the basis that we care about, the momentum basis. And then this, our operator acting on an arbitrary state. So that's P. P. Now we have the state and we choose, well, in what basis do we expand it? It's easier to expand it than the P basis because we know that this is diagonal in the P basis. So we expand it in the P basis. Oh, yes. Okay, everything is linear. So you can even bring like these two inside the integral at the same time. The lecture notes I take one at a time, but we can, yep. So now we have P, the operator P, and let's give it a different name. Let's call this P prime, just so not to confuse the integration variable. No, not here. This one, okay. Okay. Now, this P is an eigenstate of the operator, right? So if you see the definition of the operator, then the operator acting on an eigenstate just gives us the small p. So this is a number now, a real number, P. So then we have, I'll do it here. We have the integral. The P is a number. And now we have here this, right? And this, like we said many lectures ago, this is a Dirac delta. And what is the definition of this function? Is that essentially it gets rid of the integral. So the definition of this function that we saw before, and I think maybe Nuriya went over it in the tutorial, is that let's say P, some f of P, any function that depends on P, and here this whole thing is by definition just f. And it's the generalization of the, if you had this, in the discrete case, then this is just one when P equals P prime. So get rid of the sum, and this is f of P prime, right? It's just a generalization for the continuous case. And there's lots of subtleties if you care about the maths, but if you just want to do physics, this is all we need. So then we get p prime times, and this is our new wave function. At the point p prime. So let's rewrite everything. So if the momentum acts on the wave function of p, and it takes it to p times this, right? Just multiplies it by p. Good. It has these primes here because I used prime there. Okay. So this was the easy case. Similarly, you can imagine that, and you can do it at home. For the position wave function, it takes, sorry, the position operator takes the position wave function to multiplying it by x. And the other two cases that we saw last week was how they act on each other's wave functions. So we saw that it takes, if instead of seeing how p acts on the momentum wave function, you want to see how it acts on the position wave function, then it took it to, and I hope I get the signs right, x of psi of x. And here the same thing without the minus sign. Okay. So this is kind of revision. It will be useful later when we want to talk about, for example, what's the average position of some actual particle that has a given wave function, then we might need to use these things. But for now, what we use them for is to compute the commutators. And we do it once and you'll never see this again. And then we just use it as a building block, but we have to do it anyway. So questions so far? It is what it is. Okay. Good. So we're going to compute this, and I already told you that the answer is going to be that this is constant. There's a typo in the lecture notes. This thing is missing. The constant is missing. So it's a constant times the identity matrix, which is great because it's a constant. Why do we care about this? Because later on when we want to talk about in the next lecture about the evolution of, for example, the evolution of x, right? Then we apply this Schrodinger equation for observables. And if you remember this was and then the commutator with a Hamiltonian. This. And the Hamiltonian is going to depend on P, so we're going to need this as a building block to put there. And because this is constant, that thing is going to have a very nice form. Okay, so that's when it's going to pay off. So how do we compute this thing? Again. If you don't get this, don't worry, we'll come back to it after the break. So this is xp minus px. And what we do is we're going to see, again, instead of just computing this operators in abstract, which you could do as well, but instead we're just going to see how they act on the wave function. So instead what we're going to do is like see, oh, for any state, we're going to see how this acts on the wave function, and this tells us how these act on a given basis, which then we'll see that this is already sufficient because it will be constant. Okay. So remember, this is a matrix, right? Product of two matrices, subtraction, it's a matrix. So this thing is a matrix, so we can sandwich it between two states. And this is just going to be x, xp psi minus x, px psi. The hats are useful because capital P looks a lot like lowercase p, and the same for x. So this helps us distinguish them. But you don't have to write them all the time if you don't want. Okay, so then we're going to compute these two terms. Yep. And as I said, this is not something we do a lot. This one is easy because we look at this part, at the first part here. Well, this is just that because x is an eigenstate of x with eigenvalue x, little x. So then this is just little x, and then right, it's a number, so we can get it out of there. And this thing we already computed, so that's minus I h bar x dx. Right? This is a term that is done. Can you, wait, I'll point and you tell me where you mean what you mean. Wait. Yes. Oh, shit. I thought you were talking about this. Yeah. So the state is a state, right? It's a vector. We can expand it in any basis. We're going to see what happens to the coefficients in the position basis. We could also see what happens to the coefficients in the momentum basis. So, yeah, so this, sorry? Yeah, so maybe I'll just write what this is. So this one here is, this thing here is little x, big P, sorry? This is P, big P, sorry? This is x, sorry? And this thing here is P, x, sorry, right? So when I did, no. So this is just the eigenvalue operation. This is plugging in that thing. Is there still a question?
Just a quick, just to
yeah.
Recap. We assume that the eigenvalues of the x and p operator, the eigenvalues of the x and p operator are not complex.
No, they're not complex. No, this is by definition. So if you write, oh, I already erased it, but like this is the x, so x are the eigenvectors, x are the eigenvalues in the, it's only in the real line. Okay? All right. Okay, so this was the easy part. So this was one of the terms. Now we do the other term, which is much more annoying. X psi. Well, we leave this two alone for now, and we just act X expanded on X acting on psi, and we're going to expand X here. So we'll leave this two alone. And we're going to see, well, what is this thing? It's the integral, the X, X, acting on X, right? So without the X, it's just the expansion of this, and then I brought the operator inside. Okay. And now, just so that the integration variables are not the same as this, we're going to put here some dashes. Yeah. Good. All right, so we know how X acts on this. This is, again, the eigenstate. So we get X, B, and now here, this integral, the X tac, X tac, and now where this, because little x is an eigenstate of big X, we get this. Okay. But now this thing, and it's a bit clumsy the way I do it, but like this thing is a new state psi prime. Can you even see what I'm doing here? Okay. So this is a new state psi prime, right? It's a vector. And with the wave function, and the new wave function is this thing here. Right. So then all we need, continuing this, so this is X P psi prime. And that is this thing here, right? That's exactly this expression, except now our wave function is the previous wave function times X. So I'll just plug in that result here. So minus I H bar d dx of the new wave function. And what's the new wave function? It was X times the old wave function, right? That's just this, there. And now it's just the derivative of a product is the first one times the derivative of the second plus the derivative of the first times the second. So we have minus I H bar, and then what we have, let's see what order I did it. So the first one times the derivative of the second plus the second term, minus I H bar the derivative of the first times the second. This is 1, right? Just deriving X. So it's 1. So I have these two terms. Okay? And the nice thing is that now we come back here. And now we need to subtract one minus the other, and there's one that's repeated, so they're going to cancel out. Okay, so if I have so that's going to be this one. Of with the brackets minus this one that we just computed. I missed an x here. Yeah, x minus I h bar. Okay. These two terms are the same with different signs, so they just cancel each other. So then we have, yeah, it should be plus I h. So we have I h of x. Yeah. So now, let's bring it together. Okay. Questions so far? No. Okay. So now if we use the same way to express how this commutator acts on the wave function, how does it act on this basis, on the position basis? Well, it takes the wave function to the new wave function, which was this thing we just computed. But that's just this thing we have there, which is I h bar times the wave function, right? So it doesn't really change the wave function. It just adds this coefficient. And it needs to do this for all x, right? Which means that if you have your infinite vector and you apply this thing, you just get the infinite vector times all coefficients multiplied by I, which means that this thing is a constant matrix. You could have done exactly the same for the momentum wave, but this thing that this is a constant matrix. So this is just the identity, and then it just adds this. Okay? Because if it works for all the elements in the basis, then it's that. Okay. Good. So this is what's called the canonical commutation relation. It's super important. It also shows up in like Heisenberg's uncertainty relation. We'll see later. It also depends on this. Like when we later see that, what is it, dx, dp, this is gotta be larger than, I think, h bar or h bar over 2, because it will depend on the commutator. Right? And this thing you probably already heard about a few times, that you cannot know the position, the momentum of a quantum particle exactly, and it comes from here. We need a bit more complex things, but I think how does it work? No, this one ends at the time at 11, and the next one starts at 11:10. Is that correct? Yes. Question?
operator that X transpose that the operator applies.
What's transpose? Oh, sorry. I'm missing here the sign. I'll just say this is where we plug in the thing we just compute, like how the wave function evolves. Sorry. Yeah. Right. Okay. So then we have 10 minutes. We'll talk about the next step is that, I motivated all this by saying that we'll need this kind of ingredient in dynamics because the Hamiltonian will depend on X and P. But in fact, it can be any function of X and P. So it's useful to compute commutators of this formula. Any function of X times P and the other way around. So X times any function of P, and then we combine them to have any function of X, any function of P. And this might look complicated given everything we just did, but in fact, we don't need to go to do any derivatives or to go to the expansion in any basis. We just need some very simple building blocks. So now we go back to easier maths. So I'll just tell you what the ingredients are. We compute this, and then we'll compute it maybe after the break. The first one is a thing we do whenever we have a function, we just expand it to make things look a bit more linear, so that we can work with. We just expand it in some series, so from like the Taylor expansion, and right? And these are some complex coefficients. Okay, so just to be clear, this is A0, X20 is the identity matrix or operator, plus A1 A2 square, etc. And this kind of object is much easier to work with than, say, cosine of X or exponential of X. The second one that we need is just the commutator of the sum is the sum of the commutators. So if you have matrix A plus B, C, this is and if you just write everything, if you just write AC plus BC minus CA minus CB, this is just getting these two terms together, AC minus plus BC. And the last ingredient that we'll need later on is just a definition of the commutator, but I give them numbers so that later we can use them by numbers. So, well, you can write AB as BA plus the commutator. And hopefully that's the right way around. Yeah. Okay. We still have 10 minutes. Okay. So we try to compute this commutator, and a lot of quantum physics in some fields, like some kinds of condensed matter physics and so on, large part just computing commutators of different observables. Yes. But we'll see later why this is useful. Okay. So now let's do it. F any function of x. Any well-behaved enough function of x. So this is by using 1 and 2, we can expand it as this, x to the n. I just use those two ingredients together, which means that now we need to worry just about this commutator. Okay, and we'll start now. And we'll see when we have to stop. And the trick is we're going to take this first term and we're going to bring each of these x's. So this is like x to n minus 1 times x, p minus p xn. Okay? We're going to bring first this x to the other side by using this equation 3. Then we're going to bring the next one, then the next one, then the next one. And you'll see that every time you get a constant term. I think we have time to do it, so let's do it. So now by using this property 3, and I care only about this, xp equals what? Property 3 equals px plus the commutator. So we have x to n minus 1, and now we have here px plus the commutator, which is I h bar identity. Minus p xn. Okay. So now we have xn minus 1 is xn minus 2 times x. Okay. And I'm still in this first term, px plus, well, this matrix times I h bar xn minus 1. And the identity, but the identity is not doing anything here, minus x to the n. But, so the next step is going to be to bring this to the other side. So I put brackets here. And we have xn minus 2. And what we have here is this is the same as px minus the commutator. Plus the commutator, sorry. Edge identity. And on the other side, we still have this x plus this one, this identity. We don't need it. Okay. So what is this? I'll write it again. It's x n minus 2 p choke, and we have these two x's to pick up plus I h bar, and then in this term we have x n minus 2 on this side and one more x there, so it's x n minus 1. Now we still have this thing here. And the problem is that at the end, this is going to have a nice form. So the idea is that every time we bring an x to this side, we get this term that is the same, right? So then we have x, and I'll just rewrite what's there. Px squared plus 2 IH bar x n minus 1. So if you don't believe me, you can do in the break that we are like, now we bring the next one and you get one more term of this. So after we bring all of them to this side, all of the x's to the other side, what we have is p all the x's are on this side. And how many of these terms did we get? We got n terms times I h x n minus 1 minus, whoop, I forgot an n, p x n. And now we have two terms that are the same with different signs, so they cancel each other. And we're done. So this and this are the same. So I'll just finish this and then let you. I'll go for a longer break. So where did we start? We're doing this commutator of x to the n p. These terms all cancel each other, so it's just n I h bar. So all we got was we get rid of one copy of x here, and we get an n sign here. And we can write this as I to h bar like that, where this x is the capital matrix. And don't worry that it is a matrix, just think what's the derivative of something, the derivative in order of this variable to the n is n times, okay, because this is n times, and then here minus 1. It's exactly like with like real variables. And now if we put it together, and this is the last thing we'll do, we want to put it together here. So we have f of x and p. This is the sum on n, a n. And now that commutator that we just computed of I h bar ddx of x of n. And because, so this is derivative in order to this big matrix. And because nothing else here depends on x, we just bring this derivative outside. So that's derivative x of this thing x of n, and then some this constant coefficient I h bar. But that's just I h bar. I mean, this thing here, we said this was the definition of our function when we expanded first. This is 1. The x of f of x. Okay. So we did all this to find this commutator, and we're going to use it break. Well, I'll tell you how it works for the other one, and then we're going to start with dynamics after the break. So that's all for now. What time is it? Yeah. Okay, we can restart at 11 plus. No? And if there's questions, I'm here. We have this P, and we're done. For function. And if there's questions, I'm here. F of X. This will work. This will work.
Is it possible that the solution here is wrong? Because in my head, this epsilon does not, like, I get this part.
Sorry, give me the beginning. What's the context?
Exercise 4.1c.
Yeah, okay.
And you get this, and I agree, but then epsilon disappears.
Oh, yeah. Yeah, I think epsilon disappeared. Yes, I mean, wait, did you, what happens to the tau? What was epsilon to start with?
It comes from here.
These are some numbers, not a derivative even or anything. Yeah. Yeah. Then yes.
I think it's just for converting energy or something.
So what series is this? And this
4.
series 4, exercise
1c.
1c. Okay, yeah. I'll just tell them to fix this. Yeah. In fact, let me take a photo and send to them. Epsilon. Thanks.
And I don't understand this part of the solution here. So you have to find this rotation operator.
Yeah.
And you're given what it does with the 0 state and with the 1 state.
Mm-hmm. So these are the kind of the stationary states,
Yes.
right? But now the parameter is theta, is not time.
Yes.
Yeah.
And now it says, if you do it with pi halves, it transforms plus into. Oh, did that change?
Maybe she updated the
I
solution.
thought it was mine. Okay, yeah, no, then I'm good. Yes,
Okay.
then it makes sense. I thought it said minus here, plus into minus. And then I got different W1 and W0s.
Okay. Okay, but it works. All right. Okay, great. 4. So if we, no, I still give you 1 more minute, sir. No, it's not. Okay. So to recap, what we did so far was to first we computed this commutator, just vanilla x and p, with it's proportional to the identity. There is if you have such of and you compute the commutator with, then it should be the same constant times the derivative in order of x. And now we could do exactly the same the other way around. So x on the left and any function g of p on the right. And the technique is exactly the same. So you can do it at home if you want. And I can just give you the solution. Not surprising. It's totally symmetric. You just get here the derivative in order of p of your function g of p. And you get the minus sign here, right? Okay. So this was all to derive this ingredient. So if you didn't follow the first lectures so much, don't worry, this is all that you need. Okay? Because now we can finally start talking about dynamics again. Okay. So and I'll just first very slowly recap what we had, because I don't have so much to cover today even. So last time, before we went into the continuous systems, what did you see? We talked about uniform dynamics. And you saw that if the unitary is uniform on time, then this means that the Hamiltonian does not depend on time. We saw the Schrödinger equation, which I'll write again here, and hopefully there's no typos. I h bar tells us how the state changes in time. And then we saw that for time independent observables, so meaning that if I'm not moving my measurement apparatus over time, but the state is changing because there's some dynamics, then we saw that we can compute, instead of computing like the whole evolution of the state, we can just look at the evolution of this observable, like position, momentum, or spin. And we saw that it changes with the Hamiltonian, and it was, I think, I over h bar, the average change of this commutation, right? And the last thing we did was to talk about the evolution of states. So first we saw that there's some states that are stationary states. So evolution of states. So first we saw stationary states are the eigenstates of the Hamiltonian. So are these that satisfy this equation. And so this is the basis of the Hamiltonian, not like the position basis, just the basis of the energy basis. And that if you have some state, some initial state, you can always expand it in this basis. So we say, well, it's some sum in the discrete case. Okay. And if we want to evolve it, we just need to evolve each of these terms individually, and we saw that for stationary states, this just gave it a phase, I, okay, time over h bar, right? And this is how we evolved states. In the continuous case, instead of a sum, we'll have an integral here, and normally we don't call them k for the energy basis, but that's it. Okay. So now we finally can apply all of this to continuous systems. And one example is just, well, suppose I have a particle like an electron. It has some mass. It has some other properties like charge, spin. But for now, suppose that those properties don't matter. And all this electron is doing, it's kind of moving freely in space. Then what would the Hamiltonian be? And this is in general what's called the Hamiltonian of the free particle. So now this is the part where if you were physicists, it would be much easier. But not being, I think, I can still explain the basic intuition. So let's suppose we have just one particle, okay? Then we can remember that I told you that the Hamiltonian represents the energy of the particle. And you can think of it as like the kinetic energy plus potential energy. One example is seeing like, I don't know, classically I have a ball that's moving with some velocity v at some height h, and here's like the earth, and it has the kinetic energy of just being moving fast. Okay, so that's, in this case, this would be, maybe, I mean, you had some physics in high school. It would be this, so 1/2 of mv squared. And then it has some potential energy, like gravitational potential energy, which in this case, it's m times h. And for now, it could be any function of the position of the particle. And if you're in one dimension and not two, like here, it's just v any function of this. Okay. So later on, we'll see that other examples are going to be something like, we put an electron inside a box and we just have this v of x be something like v, or put it in some electric field in general, so it feels some potential in the same way that we feel gravity pulling us down. Yep. Don't worry about the details for now because we'll keep it very, very abstract. So this is classically. And in the quantum case, we just take the direct analogy. So, and this is kind of justified a posteriori, because if we define the Hamiltonian this way, then we can explain it matches the experimental observations. But the intuition is this. So this, if classically mv mass times the velocity is the momentum. Okay, so we can write the kinetic energy, instead of writing like this, we can write it as p squared over 2m. And now instead of m for the mass, we're going to call it mu, and this is just to have the consistent notation with the lecture notes and also with the book by Schumacher and Westmoreland, which I recommend on Moodle. So we have this, and the reason why I express in terms of p instead of velocity is that now we actually have a quantum a quantum operator that we call P. So what we're going to write in general is that the Hamiltonian is going to be P squared, and this is an operator, over 2 times the mass of the particle, and this is just the kinetic energy, plus something that depends on the position of the particle. Some function v of x, which we'll see many examples of this, from the simplest to things a bit more complicated. Okay. Right. Another example is, for example, if I have a nitrogen atom and you have like an electron walking around the nucleus that has a proton, it feels some potential depending on the distance. It feels this attraction. Okay. But now all we need to know is that this is a function of the operator x, and this is our operator p. So what is just plugging in that thing here. So it's p squared over 2 times the mass plus v of x times our state is I take ddt. And so far, this is still very generic. But now let's look at something a bit more concrete, which is the evolution of some observables. And now is when everything will be useful that we did before. Observe. And we're just going to apply that rule there. So ddt of some average of the observable in time is I over h bar times now the commutator of the Hamiltonian with the observable. The Hamiltonian is this, p square over 2 mu plus v of x and a. In time. And now, because the commutation is linear, we have two terms. One is I over h bar 2 mu p squared a plus I over h bar this function of x and my observable. So we have these two terms. One of them is just a commutator with p, well, p squared, and the other one is a commutator with some function of x. This will tell us how the average of some observables evolve in time. So let's see examples. For the two observables that we know so far, which are the position and the momentum. So first we do this commutator here. So we have p squared x and p squared is a function of p. So we're going to use this last building block here. So this is minus if we change the order. And we just have that g of p is p squared. So then the solution is that. Sorry. Yeah. Exactly. So the solution is minus 2 minus from this minus IH bar. Sorry, I'll do it properly. Sorry, minus IH bar ddp of this function p squared. Is that the right sign? Yes. And that's just minus IH bar, the derivative of p squared, or in order to p, it's just 2p. So that's this commutator, and now we need to do this commutator. Yeah. Did I miss someone? Yeah, you're right. Yeah, you are right. And yeah, you're right. And I think, yeah, this would be plus, and this would be plus here. And I think I missed a minus sign somewhere. I'll check later. Let's see if it works out. Yeah, let's see. The other commutator, thankfully, is 0, because this is just a function of x. Okay, meaning we can express it in this Taylor series of powers of x, and all the x's commute. So this is going to always be 0. So let's bring it together. So somewhere there's a typo in the lecture notes, but we need to do it step by step again to find out where we missed a minus sign. I'll do it explicitly then. We have time. Why is it 0? Because we have v of x is a function of x, so we expand it again. And x to the power n, which means that then when you do, v of x, x, using those building blocks from before, we get sum over n. This is from 0 to infinity. An x to the n x, right? And this is just x to the n times x minus x to the n, and that's 0. Oh. So in general, yeah, maybe I can add the here to the building blocks. I think that's useful. If you have any function of x that can be expressed as a series, or if you have any function of p, this result is going to be 0. Okay, that can be expressed as a polynomial series. So let's bring them together and see if now it works out. So we have ddt of the average of x over time. So I h bar to mu, and now this commutator that we saw was, yeah, no, this doesn't. there's definitely a minus sign missing somewhere. So it could also be missing on the evolution of observables equation. Might be that the I is below and then we get an extra minus sign. So I'll put here somewhere a minus sign that we don't know where it's coming from. Okay. That's life plus I over h bar times 0. And now here a bunch of things will cancel each other out, so we get just P over mu, average on time. Sorry, I'll write it here again. And now, why is this nice? Because classically, so again, there is some minus sign missing somewhere. But basically, what happens when you take the time derivative of x of the position, you get the velocity, and the velocity is p over the mass, right? Yeah. So it's kind of the same relation, but just for the average of this quantities. And this is why we care about this basis P in particular, that happens to be the Fourier transform of the X basis, is because then with the right Hamiltonian, it really acts like the momentum in the classical case. So now we can do the same for momentum. Momentum, like the classical moment. So the velocity, so momentum is velocity times the mass, essentially, classically. It's like if you've seen it in some high school physics, you might remember it. If not, don't worry. Okay, let's do first the momentum one. Again, we need to compute these two commutators. P squared P, luckily, is just 0. And V of x P is the minus sign that's missing. Yeah, it was either there that the minus sign should be switched, or it was in the equation for the evolution of observables, really. Because here I have minus I h minus I h dx of the effect. Okay. So up to a minus sign, you believe me? Let's put it like this and assume that the error is in the other one. So then if we, I mean, this is just any function and I just applied that rule there. So now we write it here. ddt of momentum is what? I over 2h mu average of 0 over T and now there's a minus sign here somewhere. So the first part is 0. The second part, I'll just, if there is a minus sign here that is missing, then these two cancel each other. So we get just the average on time, dx. T. All right. And I think we keep it like this. We keep it like this. Now, what is the class analogy? Classically, when you do have some situation with a potential that depends on the position, then what we call this derivative here of v of x, this is what we call the force, like the gravitational force. And if you remember this, this equation, well, force is dp dt. Okay. Which, if the mass is constant, this is d dt of mass times the velocity, which is mass times the acceleration. And if you know one physics equation, might be that force equals mass times the acceleration, right? Yeah. This? What is equal to what? This? Okay, so so this I just applied the equation for. I just applied the usual equation, this d dt of some observable, possibly with a minus sign, of h. The observable, now my observable is p. H is p squared over 2 mu plus v of x. I computed the building blocks here. Yeah?
I can see that, but why are those two equal to the vectors? Are those that just definition?
So this you believe?
No, I mean that part is.
This belief?
I'm talking agree
This?
I'm done. I understand why that one. So if we go to the right.
This thing?
That, yes.
This we derived a few weeks ago when we first talked about dynamics. We did a Schrödinger equation, then we saw how we can look at the evolution of observables, of the average values of observables. So I don't know which lection this is, but it was just before we started with the continuous system. Yeah. Okay. Good. So that's the classical analogies here, is that, you know, this P and X really act like the classical position and momentum for, at least for the case of average. So if we summarize the results, and I'll tell you on Thursday where the minus sign was missing. So the summary is what we call and I hope I'm not misspelling his name. It's Ehrenfest theorem, which just tells us how, well, the position on average, the change in position is given by momentum on average, and the change in momentum is given by the force, which is a derivative of the potential on average. And this is nice because classically you have the same equations. Sometimes we call them equations of motion that tell us. So this will tell us later how the average position of a particle changes in time and how the average momentum of a particle changes in time. Okay. We will see many examples starting on Thursday, and we'll start with a very simple case. In the tutorial, we'll already do one example. So we have lots of time left, and I already covered everything I wanted to cover. So maybe I'll just do kind of a summary of where we are in the course. Okay. So this is more like a tech tree than it is a linear progression. So I'll just make some columns here. Where we are. So this is, here we put the general formalism that we found. And then we applied it to discrete systems. And continuous systems. Okay, so what did we do? We talked about states, measurements. So we talk about measurements with respect to a basis. We talked about projective measurements. And then we talked about how to represent them as observables. Right? And states here, we just talked about vectors in some Hilbert space. This is completely abstract in general. Then we talked about dynamics, and first we just saw like any unitary dynamics, and then we went into the case of uniform dynamics. And then we saw that, well, if there's some parameter t, for example, time, such that the unitary only depends on the amount of time that has passed from the beginning to the end, then we saw, well, we have this. We have the h of t, we looked at Schrödinger equation, we saw evolution of observables, and evolution of states. You can't really just evolution of states. Okay, so we've been applying this both to discrete systems and to continuous systems, right? So here, oh, and something else we did. Still here in states was the tensor product right? Of when we have several systems. And we also talked in measurements, we talk a little bit about measurements as a physical evolution. Yep. Okay, in this SQuID case, what did we talk about? Mostly qubits. Here, for the measurements, we talked about the X and Z basis. There's also the Y basis, but yeah, it's like the ugly sibling. But it talks about, we talked about observables as the Pauli operators, X, Y, Z that can be seen as observables. And then we saw that they can also be seen as unitaries because they are unitary, so they can have can build circuits out of things like X, Y, Z, Hadamard, C naught. And it did also in the tutorial just a rotation around X by some angle theta and so on. Yep. For the observables, we also talked about the spin observables, which are the same, just multiplied by h bar over 2. Yep. So we did all this. And then we looked at some uniform dynamics. So we looked at a spin, so a qubit dynamic. And we saw only just a very simple example, right? So we saw how X, Y, and Z evolution. And we just said something like the Hamiltonian just depended directly on one of the Pauli operators. And we looked at state evolution. And we saw like how this corresponds to rotating the Bloch sphere very slowly. And now we can say the 0 state flipping to 1 and so on. Good. That's what we did for discrete systems, right? For continuous systems, we talk about this expansion of a state in these two bases. We saw how to relate these two things. We looked at this in a product. We looked at all these commutators. And this is all there. We've not talked much about dynamics. So we've not given, like here we said, oh, we actually evolve these qubits with circuits, and we've not done this yet. We've also have not done tensor products here, but we will. And the first thing, and the only thing we've seen so far is this Hamiltonian, which is p squared of 2 times the mass of X. And then we saw evolution of some observables. But this is still very abstract. So what we will do still in this, exploring this part of the lecture, we're going to look at some specific cases. So we're going to look at specific V of X, and then we're going to look at specific examples of the wave function here, so that we can get an idea of like something that is more real, like an electron that is more or less in this position. What happens if you put it in some place that has this Hamiltonian? Like, how does it change? So we need to see some examples of this, because at the end of the day, we want to do the aerogen atom, where we have the electron filling this potential, and it can move around, and we need to see the physics of this. That's one thing. Then what is still missing here, the big chunk is going to be talking about uncertainty in quantum mechanics. So when we're not sure, yeah, the Schrödinger equation is a kind of a luxury. So if we know the exact Hamiltonian of the system and we know the exact initial state, we can apply it. Realistically, most of the time we don't, right? Maybe our system is interacting with a much larger environment, and we need to have some way of just seeing like, given what I know about the quantum state, how can I evolve my knowledge? So that will be another big chunk. So it will be talking about uncertainty here. Then we'll do the uncertainty relations. We'll talk about, uncertainty in quantum states, density matrices, and uncertainty about dynamics. And that's kind of the big thing. And then we'll see how many applications we can talk about. Once we have the continuous system dynamics down, when we do the evolution of the state, then we can try to model some experiments. And one that we'll do will be the double slit experiment and this measurement of a spin experiment. Okay. So that's kind of just to situate us of where we are. And with this, I'll see you on Thursday. Yes? You found the minus sign.
You wrote down that the commutator of x in the function
Yeah.
is minus IH, the derivative.
And it's plus IH?
It is not.
IH.
Yes, it's both times plus IH
Okay.
for the commutator with the functions.
Okay.
And the Ehrenfest theorem actually has a minus sign for the momentum force.
Okay. Okay, thank you. So if you didn't hear this at home, there's a minus sign here, and there will be some, and the other one is in this commutator. Very good, thanks. Good job. Good, okay, see you on Thursday for the tutorials.